Okay, so with this definition of pumping lemma, let us now try to prove the pumping lemma. So I can say that proof of pumping lemma. Now this proof is based on certain propositions I am going to make, and the propositions are based on one of the principle of combinatorics called as Pigeonhole principle. So what does this Pigeonhole principle says? So it says that suppose I have n baskets. Okay, suppose I have n baskets and I have more than n balls. So number of balls to put in one basket, to put in these baskets is greater than or equal to n. That means the number of baskets. Okay, then the pigeonhole principle says that at least one basket will have more than one ball. Understood? Because suppose I have n plus more than one ball. Because suppose I have n plus 1 balls, then even if I put in every basket I put one ball, I am remaining, so I'll be so one ball is left, and that I have to fill it in one of the basket. So one of the basket will contain at least more than one ball. Okay, so this is the pigeonhole principle. Now let us try to map this principle to our pumping lemma. So what does this pumping lemma says? Pumping lemma says that if there exists a string whose length is, which is accepted by a given FSM having n states, and whose length of the string is greater than or equal to the number of states of the FSM. So what will happen? So the FSM will consume one symbol after another and continues to make its transition from one state to another. So if it has to consume more than n symbols, capital N symbols, that means it has to move, this implies it has to move, the FSM has to go through certain states more than once. Understood? More than once. And this implies that the finite automata has at least one cycle. Understood? Any doubt? It can have more than one cycle, but the proposition is if the finite automata is accepting a string whose length is greater than the number of the states of the automata, then the automata should have at least one cycle, okay, to consume those extra symbols. Okay, so let me write it in a proper fashion. So my proposition is any string, so let me write it in, if any state machine accepts, so FSM actually, finite state machine accepts a string whose length is greater or equal to the total number of states, this implies the finite automata will have at least one cycle. Okay, so let us build our proof based on this proposition. Okay, so suppose I have a string, so suppose I have a string W which is represented as X, Y and Z. Suppose the finite state automata initially is at S0. Okay, so this portion of the automata suppose consumes X and it reach at suppose Sk. Okay, then what happens? So with the proposition I am assuming that it has at least one cycle. So suppose it goes back and come again to Sk. Okay, to consume the symbol Y, substring Y. Okay, then from Sk I can make a transition to reach at the final state Sf. Okay, and accept the entire string XYZ. Understood? So I can say that what will be my extended transition function to consume XYZ. So for this finite state automata, the extended transition function represented as delta star. So what is the current state is S0, and what is the string I am processing, that is X, Y and Z. So this is equal to what happens. So first it consumes X, so I can say that it will be, so this is X, this is Y and this is Z. So I can say that it will be finally, it will be, so I can say that first it has to, just a second, let me write it in here. So you have to put extended transition over S0 and X. So whatever is that, then you have to again apply extended transition function over this thing with Y, and whatever is the final, whatever is the state, we have to apply this thing, extended transition function for Z. Understood? Any doubt? So you decompose the string as XYZ. So first I have to consume X, that means I have to apply the extended transition function. Starting state is S0 and I have to consume X. So what is this extended transition function of S0 comma X? So it will be, you can say it will be delta star of so S0 comma X is Sk, so it will be Sk comma Y and that with Z. Now what is Sk comma Y? Now since there is a cycle, so the final state I will reach after consuming the substring Y will remain as Sk. So I can say that it will be delta star Sk comma Z, and hence it will be Sf. So this way we apply the extended transition function for the string XYZ. Now let us take a value of Y. Suppose Y is equal to 2. Then what will happen? Then X, Y to the power 2 Z is my new string W1. Okay. Now if I apply the extended transition function over X, Y to the power 2 Z, then what will happen? So first after consuming X it will reach to Sk. Now it will consume the substring S into that is Y into Y, that is the concatenation of the substring Y with itself, by making 2 cycles in this FSM. Okay, and it will remain in Sk. So I can say that delta star, so I can say that delta star of Sk with Y square is same as Sk. Okay. So if that is the case, then what will be the final state I am reaching after processing X, Y to the power 2 Z? So it will be Sk with Z, and hence it is Sf. This implies that X, Y to the power 2 Z also belongs to the language L. Okay. Then you can apply the mathematical induction to prove that if if it satisfies for k, it will also satisfies for k plus 1. So this is the normal way to prove a pumping lemma. Okay, any doubt?